So consider a function f of x equal to a minus x times b minus x, quantity squared. And we are told that 0 is less than 2a is less than b. So that a and b are both positive and b is bigger than twice a. All right. There are two critical points. And critical points that are given to us, or critical values, they are b comma f of b. Okay, it's kind of, I mean, well, so, okay, that's that. I feel like that's kind of supposed to be, I feel like they're trying to hide something from us there. And the other one is b plus 2a over 3, comma, 4 times a minus b cubed over 27. And the question is, determine if the critical point is a local determine if this critical point is a local maximum, a local minimum, or neither. Okay. Notice we don't have the first derivative, right? They didn't give it to us. I feel like we might have to find it. Like I don't feel like there's a way to do this without finding the first derivative, which is fine. I will also mention, what is f of b? If I plug in b to this function, what do I get? Well,
0?
Yeah, it's 0. Not that that really changes anything, but it is good to be aware of. So I want to know if this point here is a max, a min, or neither. So I probably need to use the first derivative test, which means I need to take the first derivative. So the first derivative is going to be, I'm going to use the product rule. Remember, we have a function of x. A and b are constants. So I'm going to use the product rule. So the derivative of a minus x is -1 times the other part left alone plus a minus x times the derivative of this, which is 2 times my stuff to the first power times the derivative of this stuff, which is -1. And normally I would then set it equal to 0 and find the critical values, but they already told us what the critical values were. So let's not do that. So I want to determine if this is a, oh, I see, That's a good question. So I want to put these critical values on my number line. B and b plus 2a over 3. Which one's bigger? Is b bigger or is b plus 2a over 3 bigger? That's kind of hard to answer, right? Because I need to put them on the number line to see like where it's increasing, where it's decreasing, etc. Well, they give us that b is bigger than 2a, or that 2a is less than b. So here's what we can say. We can say that this here is definitely less than b plus b over 3, because 2a is less than b, which is less than 2, or which is equal to 2/3 b. So this is definitely less than b. Interesting. So on our number line here, we've got b plus 2a over 3 and b. So the hard part for these problems is like, now what do you plug in to figure out if it's positive or negative over here? Right, that can be challenging. So we know that b and a are both positive. So often if I'm trying to pick something bigger than a letter that's positive, I pick twice that letter. So I could plug in 2b. That'll work. So I plug in 2b. Except, so here's what we have to do one more step. And this is something you normally have to do anyway. We should have probably factored this. I can factor out a b minus x from here and a b minus x from here. I can also factor out a -1. So let's factor out the -1 and the b minus x. From this first term, I'm left with a b minus x. From this second term, I'm left with a minus x times a 2. Now I'm running out of room. Okay, I'm going to erase this part over here. So simplifying this part inside here, I've got a -1 times b minus x, and then I've got a 2a plus b, and then a minus 2x. I made a mistake. It's a small one, but there is a mistake. I mean, it's just in this last step here. It's not 2a plus b minus 2x. It's 2a plus b minus x minus 2x, which is minus 3x. Now, how did I know I made a mistake? Well, I knew that b plus 2a over 3 was supposed to be a critical value. So if I was trying to solve this part equal to 0, I should get 2a plus b divided by the coefficient of x here, which is 2a plus b divided by 3. But when I had a 2, I was like, oh, that's not matching up with that over there. So it's good to think about what's going on. All right, so now I pick something larger than b, like 2b. So I plug in 2b, negative, 2a plus b minus 3 times 2b, that's going to be 2a, b minus 6b is minus 5b, but 2a is less than b, so this is going to be less than b minus 5b, which is negative 4b, and since b is positive, negative 4b is negative. So this is negative, negative, negative. The whole thing is negative. Interesting. Okay, now for the harder part, picking something between b plus 2a over 3 and b. I'm not sure. So here's what I'm going to think about. I'm going to use this here, and I'm going to so I'm going to say I want to pick something between b plus 2a over 3 and b, which is 3b over 3. Yeah. I mean, I think this is the only way to do this. I don't actually know, but this seems reasonable. The only problem is I know that 2a is less than b, so I know. Oh, look. Yeah. So good. So this is less than, well, 2a is less than b, so this is less than b plus b over 3, which is 2b over 3, and that's definitely less than 3b over 3. So 2b over 3, that's the number I'm going to pick in here to test if my first derivative is positive or negative. This is a well-designed but tricky question. So if I plug in 2/3 b, this part's negative still. B minus 2/3 b is positive. And then, okay, so now I'm going to have 2a plus b minus 3 times 2/3 b. All right, 3 times 2/3 is 2, so this is going to be 2a plus b minus 2b. This is going to be 2a minus b, but since 2a is less than b, this is less than b minus b, which is 0. So this is less than 0, so this part here is negative. So it's negative, positive, negative, which means overall it is positive. So left of b it's increasing, right of b it's decreasing. That means we have a relative maximum at the critical value b comma 0. That is not an easy question. This might have been the harder way to do it, meaning we could have alternatively tried to take the second derivative and use the second derivative test. I'm going to do that because I want to actually see if it's if it's the way we should have done or not, with a good reason. So let's look at our first derivative here. Let's go over to the other side. Let's take the second derivative. So the first derivative is, do I want the factored form? I really don't. I want the unfactored form. I want the -1 times b minus x squared plus, let's say minus 2 times a minus x times b minus x. All right, that's what I'm doing. Minus 2. Okay, let's take the second derivative. Let's factor out the -1. Now let's take the second derivative. So the derivative of this is 2 times b minus x to the first times -1 plus 2 times the derivative of this, if you use the product rule, derivative of that is -1 times that plus this times the derivative of that. Okay. And now we're going to try using the second derivative test, where you just plug in the point, and if it's positive, it's concave up, which means you have a minimum, and if it's negative, it's concave down, which means you have a maximum. So if I plug in b, let's see what we get. You get -1 times, that's going to be 0. That's going to be 0. So we get -1 times times a minus b times -1. So this is equal to 2 times a minus b, but since 2a is less than b, a is definitely less than b. So since a is less than 2a is less than b, a minus b has to be negative. So since the second derivative is negative, it's concave down, which means we have a relative maximum. So in retrospect, this is probably what the person who wrote the question intended for you to do. Not that you couldn't do it the other way, but the other way was definitely harder. So it's good to be aware, right, that there are different ways of showing you have a relative max or a relative min. You have the first derivative test where you show it's increasing here, decreasing here, or you have the second derivative test where you show that the second derivative at your critical value is negative to show it's a relative maximum. Interesting question. Are there questions about this question? Okay. So if you guys, I'm gonna start with problem 6 unless there's something else you want to see.
I have a quick question.
Go ahead.
For I'm a little confused on how you got the critical points to B.
So they were given in the problem.
Yeah.
So they were just given to me.
Wait.
I didn't find them.
The critical points are the ones at the top, right? The B plus 2A over 3 and then 4.
Right. So we can find them, but I'm going to tell you, right, in this particular problem, they were given to us as known information. So the problem I'm reading, which is number 11 here, right, they give us that the critical points are B comma f of B and B plus 2A over 3 comma 4 times A minus B cubed over 27.
Oh, okay. I got confused
Sure.
on the one of them. Okay, thank you.
Now, I will say, Emily, I think that's who's talking. We could still find them, right? If I look at my first derivative here, right? If I set that equal to 0, I'm going to get exactly x equal to b from this part, and from this part, I'm going to get exactly x equal to b plus 2a over 3.
Mm-hmm. I just didn't see the B. That's why I got confused.
Oh, sure. But I think yeah, the intention of this problem was to more check to probably to make you use the second derivative test instead of having to worry about finding the critical values.
Okay, thank you.
You're welcome. Yeah. That's a good question. It's a tricky question, but so I probably decided to use the first derivative test there because I was worried that the second derivative test would be inconclusive. But what I probably should have done was realize that taking the second derivative wasn't going to be that terrible. So even if it was inconclusive, it was probably worth it to take the second derivative to see if it worked instead of having to do the work we tried to do with the first derivative. So if the second derivative doesn't look too awful to take, I would recommend trying to use the second derivative test if it looks like the first derivative test is going to be weird where you're trying to like plug in values that aren't really values. So I had to really think about what was between A and B or whatever. All right, let's look at number 6 on this handout, which is just finding the derivative of the following. F of x equal to x squared times e to the 2 minus x. So let's find df dx is how it's written, or f prime of x if you prefer. This is going to be 2x times e to the 2 minus x plus x squared times the derivative e to the 2 minus x is e to the 2 minus x times negative 1. And that's all this question asks. I feel like this question doesn't ask enough, so I'm going to expand on it a little bit. I'm going to say find the critical values, find and classify any critical values. So to find the critical values, we set the derivative equal to 0. I should really say we set it equal to 0 or where it's undefined, but powers of x that are positive and e to the stuff is never undefined, so it's never going to be undefined. To solve this equal to 0, I'm going to factor out an x and an e to the 2 minus x. So I factor out an x times e to the 2 minus x. Here I'm left with a 2. Here I'm left with a minus 1 times an x. So my critical values are 0 from this part and positive 2 from this part. E to the whatever is never equal to 0, so it's not going to give me another critical value. So my critical values here are x equal to 0 and x equal to 2. Great. Here I definitely would use the first derivative test because determining where the first derivative is positive or negative is going to be pretty straightforward. So let's put 0 and 2 on our number line for the first derivative. And let's see, if I pick a number larger than 2, like 5, 5 is positive. E to the anything is positive, even if to a negative power. E to the negative 3 is positive. And 2 minus 5 is negative. So a positive times a negative, which means it's negative. And then you can either use the fact that 2 came from this factor, which has an odd power, which means the sign is going to change, or you can just pick a number between 0 and 2. If I pick 1, positive, 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 the whole thing's positive. And then if you pick something smaller than 0, like negative 1, it's going to be a negative times a positive, which will be negative. So it's decreasing, increasing, decreasing. So we have a relative maximum at x equal to 2. We have a relative minimum at x equal to 0. If someone specifically asked for the critical point, I would say the critical point is a maximum, a relative maximum at 2 comma f of 2, which would be 2 comma, if I plug in 2 here, I get 4 times e to the 0, which is just 4. And I have a relative minimum at 0 comma f of 0, which is going to be 0 comma, if I plug in 0, I get 0 times whatever is 0. So be careful. If they ask for a critical value, they typically mean just the x value. If they ask for the critical point, they mean the x and y coordinate that make up the entire point. Okay. Should we find the inflection points? Why not? Here's my piece of advice for finding the second derivative. So my first derivative, I'm going to write it both ways. So here's my first derivative. So I'm going to write it as 2x e to the 2 minus x minus x squared e to the 2 minus x. Or you have this, x e to the 2 minus x times 2 minus x. Oh, sorry, I wrote this backwards. Sorry, I switched my x squared and my 2x. Apologies. Okay. So which one of these would I rather take the derivative of? Well, for this one, I'm going to have to use the triple product rule. And while that is something we know, it's something I don't always want to have to use. So if it was up to me, I'd probably use this version that's not factored to take the derivative of. You can take the derivative of either one to get the second derivative, but I think it's easier to deal with this one. You might disagree, that's okay. So taking the second derivative, well, there is something that's going to make it easier, I think. So the derivative of 2x e to the 2 minus x, I'm going to use the product rule. So I'm going to get 2 times e to the 2 minus x plus 2x times e to the 2 minus x times the derivative of 2 minus x, which is negative 1. And here's the part that I think is easier. Now we're going to take the derivative of x squared times e to the 2 minus x. We already did that. The derivative of x squared times e to the 2 minus x is f prime. So the derivative of x squared times e to the 2 minus x is all of this. Do make sure, since it's minus a product rule, I'm sorry, no, it was minus there, sorry, that you end up distributing this minus sign to both pieces. So let's see, simplifying this, I've got 2 times e to the 2 minus x plus 2x, sorry, minus 2x e to the 2 minus x minus 2x e to the 2 minus x. Minus and minus is plus x squared e to the 2 minus x. Okay, now we're going to factor. We're going to factor out e to the 2 minus x. And that's the only thing we can really factor out. So I'm going to factor out e to the 2 minus x. And I'm left with an x squared minus 2x is minus 4x plus 2. Okay. So I have to use the quadratic formula to find my critical values of the second derivative here. Which isn't terrible, but it's really terrible. So we're going to set that equal to 0, but that doesn't factor. So my critical values are going to be x equal to negative b plus or minus the square root of b squared, so negative 4 squared is 16, minus 4 times a is 1 times c is 2, all over 2 times a. So my critical values are 4 plus or minus the square root of 16 minus 8, all over 2, which is 2 plus or minus 2 root 2, all over 2, which is 1 plus or minus the square root of 2. So those are my critical values, and now we have to technically check to see if they're inflection points. I'm going to make the number line, and I'll put these values on. So I've got 1 plus root 2 and 1 minus root 2. Now I'm going to plug into the second derivative. So this is where we have to be kind of careful about how we pick our points. Pick something bigger than 1 plus the square root of 2. It doesn't have to be the smallest thing that's bigger. Pick anything that's bigger, like a billion. If you plug in a billion, e to the anything is positive. A billion squared minus 4 billion is definitely positive, so it's a positive times a positive. Okay, what's the only easy number to pick between 1 plus the square root of 2 and 1 minus the square root of 2? Oh, it's 1. I pick 1, this is positive, and 1 minus 4 plus 2 is negative. And then pick something less than 1 minus the square root of square root of 2, like, I don't know, negative 20. This part's positive. This part's 400 plus 80 plus 2 is definitely positive. Maybe I would pick negative 10. That would be easier. So it's definitely concave up, concave down, concave up. So I have an inflection point at both of these values. I have an inflection point at 1 plus root 2, and I have an inflection point at 1 minus root 2. Okay. Let's not graph it. Oh, let's graph it. Fine. You guys convinced me. We'll graph it. I know I just erased like all the important part for the graphing, but it's in my brain, so it's okay. And it's right there. So we had a relative maximum at 2, f of 2. We had a relative minimum at 0, 0. So we know it's decreasing, increasing, decreasing. Sure. And so I know I just drew the whole thing. There's my relative max, there's my relative min. This is the only x-intercept, right? If x is 0, you get 0. There's no other way this will equal 0. And remember, I know here's the sign chart for my first derivative. Negative, positive, negative. And then we have inflection points, right? There's an inflection point at 1 minus a number and at 1 plus a number. Those are my inflection points right there. You might be wondering, how do I know there's a horizontal asymptote there? Well, here's what I know. I know that this function is decreasing after this, but I also know there's no x-intercepts. So you got to have this horizontal asymptote. Another way you could find it, which is a good question, is how do you figure out what's happening as x goes to infinity? You take the limit. So if I want to find the horizontal asymptote, you take the limit as x goes to either plus or negative infinity. But here we're going to look to the right. Oh, look. It's an indeterminate form. It's x squared, which is going to infinity, times e to the 2 minus x, which is going to e to the negative infinity, which is going to 0. So we have an infinity times a 0. Good times. Everybody loves an infinity times a 0. So we're going to rewrite this as the limit as x goes to infinity of x squared over e to the negative 2 plus x, or x minus 2. Right, when you bring something down to the denominator, the sign of its exponent changes from positive to negative. And now we can use L'Hopital's rule a couple times. Take the limit as x goes to infinity. Derivative of the top is 2x. The derivative of e to the x minus 2 is e to the x minus 2. And then do it again, because it's still infinity over infinity. You get the limit as x goes to infinity of 2 over e to the x minus 2. And this is going to go to 0, because the top is 2 and the bottom is getting infinitely large. Okay, that was a lot more than this question really meant for us to do, but it was good to look at all this. Questions about this? Right. Look at the next one. I will say, not that all of you have Karana, but I do think she writes some very intelligent questions. Oh, can we do 13? Sure. Yeah, 13. I was really, okay, we'll come back to 7 later. 13. So here's the question, which I'll write down. Are there values for A and B? So values for A and B that will make the function below f of x. What have we got here? F of x continuous for all x. And the function is a piecewise function. It is negative 2x plus a when x is less than negative 1. It is negative x squared plus 2x minus 3 when x is between negative 1 and 3. And it is x plus b when x is greater than 3. So a couple things I will point out before we get going on this one. thing one, this function isn't undefined anywhere, right? In each of these, and again, a and b are just constants. Negative 2x plus a is just a line. It's defined everywhere. Negative x squared plus 2x minus 3 is a parabola. It's defined everywhere on this domain. And x plus b is a line. It's defined everywhere. So the only issue we're going to have here is if when you come at negative 1 from the left and come at negative 1 from the right, these things might not equal each other. So what we need to be true is we need the limit as x approaches negative 1 from the left of this function. We need that to equal the limit as x approaches negative 1 from the right. Now this is going to just end up amounting to plugging in negative 1 here and negative 1 here and setting them equal to each other. But I get the impression your teacher would probably like you to talk about the fact that you need the limits to be equal because that's part of the definition of continuity. So if I take the limit as x goes to negative 1 of f of x, that's going to be the limit as x goes to negative 1 from the left. If I'm approaching negative 1 from the left, that means I'm less than negative 1, which means I have to use this piece of the function. If I'm approaching negative 1 from the right, I have to use this piece of the function because that's where x is bigger than negative 1. And then we evaluate the limits by just plugging in negative 1. So I will say again, you totally probably could have skipped this part and just said, okay, I'm going to plug in negative 1 here, I'm going to plug in negative 1 here and set them equal to each other. So let's see, what do I get? I'm going to get negative 2 times negative 1, so 2 plus a equals, plug in negative 1 here. Negative 1 squared is negative 1, plus 2 times negative 1 is negative 2 minus 3. So solving for a, I get a equal to negative 1 minus 2 minus 3 minus 2, which is going to be negative 8. Right, 2 minus 8 equals negative 6, yeah. Okay. Now we have to do the same thing for 3. So I'm going to kind of skip, so we would do the right, we would say the limit as x goes to 3 from the left of f of x has to equal the limit as x goes to 3 from the right of f of x. As x approaches 3 from the left, we're going to be using this piece of the function, and then we're going to plug in 3 for x. So we're going to get negative 3 squared plus 2 times 3 minus 3. And plugging in 3 from the right, we're going to get 3 plus b. So it looks like we can solve for b here. I'm going to get, let's see, negative 9 plus 6 minus 3 equals 3 plus b. So that's negative 3 minus 3 is negative 6 minus another 3 is negative 9. So these particular values of a and b do make this function continuous. And if you wanted to, if you were curious, you could actually graph it. Well, no, you could graph it. It just takes a little bit of work on Desmos to do it. Yeah. Cool.
I have a question.
Yeah.
Even though like you're not really like doing like the whole like limit process, but you still like talk about limits, like how did you know it's involving limits?
Well, because they asked about the function being continuous.
Okay, so that like it's saying, oh, okay, because that's like kind of like the endpoints of like.
Right. So specifically for a piecewise function, I know that this piece here, this line, I know it's continuous everywhere x is less than negative 1. And I know this parabola is continuous everywhere between negative 1 and 3. And I know this line is continuous everywhere bigger than 3, because they're all just functions that are normally continuous. But what I don't know is if they're meeting up when you change from one to the other. So that's why I'm asking, is it continuous at negative 1? Well, to be continuous at negative 1, the function has to exist there. Well, it does. It definitely exists at negative 1. Right? I didn't even check that because I already knew it existed there. And 2, the limit has to exist. So we had said, the limit has to exist, which means the left-hand limit has to equal the right-hand limit. So that's why we set the left-hand limit equal to the right-hand limit and then solve for a. I should point out, so the limit does exist, and the limit is negative 6, and the function is also negative 6 if you plug in negative 1. If I plug in negative 1, here I get negative 1 squared minus 2 minus 3, which is negative 1. If I plug in negative 1 here, I get 2 minus 8, which is also negative 6. That's showing me the limit from the right and the left are the same, and also that f of negative 1 is the same value. So I was using the limit part of continuity to say, oh, I know the limits have to be equal to each other. That's going to let me solve for what a and b have to be.
Okay, thank you.
You're welcome, yeah. So, but in general, if someone says show something's continuous somewhere, it means the function has to exist there, the limit has to exist there, which means the left and the right limit have to match up, and they have to be equal to each other. All right. Look at problem 7. So evaluate the limit as x goes to 0 of sine of x to the 2017th power. Wow. Okay. Divided by sine of x to the 2017th power. That looks terrible. So it also says in the problem, this is really clever and also totally doable. All right, so what do I see when I plug in 0? I see 0 over 0, right? 0 to a power is 0, sine of 0 is 0, sine of 0 is 0, 0 to the power is 0. So this is a 0 over 0 type. So it means I probably should try using L'Hopital's rule. Maybe something nice will happen. I'm going to use L'Hopital's rule. Right, so, and this is very much if you're not sure what to do, you just have to try something, right? I don't know this is going to work. I think it might work, but I really, really don't know. I haven't done this problem before. There are other things we could try, but I'm going to try this. So take the derivative of the top. The derivative of sine of some stuff is cosine of the stuff times the derivative of the stuff. And the derivative of x to the power is that power times x to the 1 less power. Okay. Divided by, now we're going to take the derivative of some stuff to the 2017 power. This would be 2017 times your stuff to the 2016th power times the derivative of your stuff, which is cosine of x. Okay, I think I see what's going to happen here. Can I cancel anything? Yeah, I can cancel 2017. All right, now I'm gonna rewrite this in a way that's kind of helpful. I'm gonna keep my cosines together, so it's going to be the limit as x goes to 0 of cosine of x to the 2017 divided by cosine of x. Sadly, we can't simplify this, it just is what it is. And then I've got x to the 2016 over sine of x to the 2016. Well, when you have things that are to the same power divided, you could write, like, if I have something to a power or something to a power, I could write this as x over sine of x all to that power. So I could rewrite this as the limit as x goes to 0 of cosine of x to the 2017 power over cosine of x times x over sine of x to the 2016th power. All right, somebody should be able to tell me what's the limit as x goes to 0 of x over sine of x.
1.
0. Right, it's 1. So then we're actually done, because cosine of 0 is 1, cosine of 0 is 1, and the limit of this part is also 1 to the 2016 power. This is just 1. Interesting. Okay, let's look at some other ones. So I could grab one of those longer questions. Let's time this. Oh, we got time. Let's look at this next one. Limit as x goes to infinity of the square root of x over x squared plus 1. And the question says, evaluate the following limit or explain why it does not exist. So first of all, this is an indeterminate form. This is definitely an infinity over infinity. Do I need to use L'Hopital's rule? Well, I could use L'Hopital's rule, sure. Do I need to? Probably not. If you wanted to, so here's one way you could go. Here's the way I would probably choose to go. This is the limit as x goes to infinity. I'm just going to divide everything by the highest power of x in the denominator. I'm going to divide everything by x squared. So in the denominator, I'm going to have x squared over x squared plus 1 over x squared. In the numerator, I'm going to have x to the 1/2 over x squared. This is going to equal the limit as x goes to infinity of x to the 1/2 over x squared reduces to 1 over x to the 3/2 power. X squared over x squared is 1. 1 over x squared over x squared. And then the limit of this, 1 over something that's getting really big, is going to be 0. And the limit of this, 1 over something that's getting really big, is going to be 0. This is going to be 0 over 1 plus 0, which is 0 divided by 1, which is 0. So the limit here is 0. You also could have used L'Hopital's rule. Right? You totally could have done this as derivative of the top. So derivative of x to the 1/2 is 1/2 x to the negative 1/2. Derivative of the bottom, which is 2x. Now this is where people might make a mistake. And they might say, oh, I have an infinity over infinity. I'm going to use L'Hopital's rule again. I don't have infinity over infinity anymore. But if I rewrite this, I've got the limit as x goes to infinity of 2x on the bottom. And I'm going to write 1/2 times x to the minus 1/2 as 1 over 2 times x to the 1/2 or the square root of x. And now you might see that, okay, what do I have on top? Where's the top part going to? Where's all that going to?
Yeah.
Right. Where's the bottom going to?
Infinity.
Infinity. What's 0 divided by infinity? 0. Right? A really small number divided by a really big number is still really small. Right, so 0 divided by infinity is 0. Or a small thing divided by a very large thing is getting very, very small. You could have also simplified this further, but you didn't really need to. But if you wanted to, you totally could have rewritten this as the limit as x goes to 0 of 1 over 2 root x. Divided by 2x is like multiplying by 1 over 2x. And then this is the limit as x goes to, infinity, not 0, of 1 over 4 times x to the 3/2. That is infinity on the bottom, so the whole thing's 0. I don't think you should do it this way, but you could do it this way. I wouldn't use L'Hopital's rule, usually unless I really had to. Let me take a look here. That's a good question. Yeah, sure. Find the equation of the tangent line to, yeah, I know what I should do next. What do I got here? X cubed plus 2xy plus y squared equal to 9 at 1, 2. So to find the equation of a line, we need a point. Got it. Need a slope. Don't got it. Find the slope. We need the derivative. But obviously, we're going to have to use implicit differentiation here to find the derivative. So we take the derivative with respect to x. So we get 3x squared plus the derivative of 2xy, I'm going to use the product rule. Just be the derivative of 2x, which is 2 times y, plus 2x times the derivative of y, which is y prime. Derivative of y squared is 2 times my stuff times the derivative of my stuff. And the derivative of 9 is 0. Okay, I'm trying to solve y prime. Now here's the thing. I only care about finding y prime at this point. So I'm going to just plug in the point right now. I'm going to plug in 1 for x and 2 for y. So I have 3 times 1 squared, which is just 3, plus 2 times 2, which is 4, plus 2 times 1 times y prime, which is 2y prime, plus 2 times 2 times y prime, which is 4y prime, equal to 0. So I have 6y prime plus 7 equals 0. So 6y prime equals negative 7. So y prime equals negative 6. It's negative 7 over 6. You also could have solved for y prime the long way, right? You could have actually isolated y prime. So you could have said 2x y prime plus 2y y prime equals negative 3x squared minus 2xy. 2y, sorry. And then factor out the y prime. The y prime times 2x plus 2y equals negative 3x squared minus 2y. And then divided by this. So you get negative 3x squared minus 2y all over 2x plus 2y. But then if you plug in 1 for x and 2 for y, you get negative 3 minus 4, which is negative 7, over 2 plus 4, which is 6. So you get negative 7, 6. Either way is fine. I just feel like it's easier this way. And then finally, to answer the question, the equation of our line is going to be y minus the y coordinate equal to the slope times x minus the x coordinate. Okay. Sure. Yeah, let's go back and look at some of these longer questions. Yeah, this problem seems reasonable. Okay, I'm going to look at problem 2 from this review. So here's the setup. A strain of bacteria reproduces asexually every half hour. So that is every half hour, each bacteria cell splits into 2 cells. So the population doubles every half hour. Suppose that only 1/3 of the bacteria survive to reproduce each generation. So only 1/3 survive to produce each generation, to reproduce each generation. And the initial population is 1,000 bacteria. Okay. The first question here is, find a recursion relation to describe the size of the bacterial population. So again, a recursion relation means you're saying the population at time t plus 1 is some function of what the population was previously. To me personally, I would probably start by just writing out some of the populations were. So I know that, right, so when the time is the first half hour, I feel like a half hour is a terrible amount of time. So when t equals 1, so t is measured in half hours. So when t equals 0, the number of bacteria you have is 1,000. Okay, so then after 1/2 hour, how many are we going to have after that? Well, only a third survive. It would have been nice if we picked the number that started with a multiple of 3. Oh well. So only a third of them survive, and then each of those split into 2. So it looks like after a half hour, we're going to have a third of 1,000 times 2, or 2/3 of 1,000. And then after another half hour, the same thing's going to happen. We're going to have 2/3 of what we had before. Right? Because again, however much we had here, a third of them are going to survive. So we're going to have a third of 2/3 of 1,000, but then they're going to double. So we're going to have 2/3 of 2/3 of 1,000. Which doesn't look good for the bacteria, right? It doesn't look like they're going to make it, because every time you're going to have 2/3 of what you had before. But here's what we can say about the population. So we can see that the population at the next time increment is going to equal 2/3 of the previous time increment, or 1/3 of what we had, then double. Questions about this? It's like, no, but I'm leaving. Sorry. Okay, the second question. Find a solution/function equation to describe the population. So this part is more where, this is where I'm writing out the values, right? Because getting it from this is usually not really straightforward, if even possible. If we write out some values, we're like, okay, well, I can see that at time equals 0, I've got 1,000. At time equals 1, I've got 2/3 times 1,000. At time equals 2, I've got 2/3 squared times 1,000. Every time increment, I'm multiplying by another 2/3. So it looks to me like the amount of bacteria I have at time t is 2/3 to the t times 1,000. Again, where t is measured in half hours, right? You do kind of have to be specific about what your t is representing. So t equals 1 is equivalent to 1/2 hour. All right, third question. Given that the initial population is 1,000, how large will the colony be after a very long time? So the question they're really asking without saying is, what's the limit as t goes to infinity of n sub t? Or what's the limit as t goes to infinity of 2/3 to the t times 1,000? Oh, excuse me. Sorry about that. So, thank you. Appreciate it. So let me ask you guys, if you have 2/3 to a really big power, what's going to happen to that number? What happens when you do 2/3 times 2/3 times 2/3 times 2/3 times 2/3, et cetera, et cetera, et cetera?
0.
You get 0. So any number that's between -1 and 1 raised to a power that's getting infinitely large, that's going to go to 0. Which again makes sense, right? If we're getting 2/3 of the bacteria at each iteration, we're getting less and less bacteria every time. So the population is getting smaller and smaller. It's eventually going to die out. I feel like I had another one that looked like it was really interesting. Oh, sure. Let's do this one. I'm going to skip to 4 and then we'll go back to 3. So I definitely feel like these questions I'm looking at are really asking you to be more thoughtful, not just apply mathematical process. So this next question is the height h of a certain species of a tree is related to its diameter by the equation. I wonder if this is true. Probably not. It's probably just made up. Oh yeah, it's definitely made up. The top of this says like all this stuff's made up. I'm not a biologist. Yeah, it's all made up. None of it's true. Okay. By the height is a constant c times d to the 2/3 power, where c is greater than 0. The relationship will appear linear when log h is plotted as a function of log d. True or false? So true or false? this will appear linear when we plot log of h versus log of d. And I have to imagine that she's not just looking for you to say true or false. I would imagine she's expecting some sort of explanation here. And it probably says that at the top of the test. Let's see. It doesn't, but I'm going to go with that anyway. Okay, so yeah. All right. So here's what I would do. I would take log of both sides. So log of h equals log of c times d to the 2/3 power. And then I use the log rules. So this is equal to log of c plus log of d to the 2/3. And then I can say that log of h is equal to log of c plus 2/3 times log of d. So is this linear? Is log h plotted versus log d going to be a linear thing? Well, yeah, because log h equals some slope times log d plus some intercept. So if you want, you can change the, like, right, you could say log h is capital H and log d is capital D. Then we definitely have that capital H is equal to 2/3 d plus some constant. Let me ask a different question because I think this is interesting. And also I know it's been a while since any of us have talked about log, or semi-log stuff. What if it was the same question, but now I said that the height of the tree is some other constant times not the capital H, the lowercase h, the actual height of the tree is some constant times 2 to the circumference, diameter. What if that was our equation instead? And we ask the same question. Is this linear when we plot log of h versus log of d? The answer is obviously going to be no, because, right, it would have to be kind of the same for the same thing to be true. Well, let's see why. So we take the log of both sides. And let's see, if I take, so log of h equals, I'm going to break this up, log of b plus log of 2 to the d power. And then if I bring down the d, I get log of h equal to, I'm going to write this so that the variable comes first. And this is log of 2 times d plus log of b. And now look, log of d is not a linear function of log of d. I don't have a log of d showing up here. So the answer here would be false. What this would be the answer to is that log of h plotted versus just d is going to be linear. So this goes back to the thing that we learned a while ago, that exponential functions have semi-log plots that are linear, or semi-log or log linear plots that are linear. Whereas power functions, where you have your variable to a power, have log plots that are linear. Good to remember that. Okay, but you can always find out by just taking the log of both sides and then seeing, oh, am I getting a linear thing with log of h and log of my d, or am I getting a linear thing with log of h and just d? That's the difference. Okay, that's a good question. Let's look at, I want to look at this one. There's one here that I kind of feel like we should do, but I feel like it's going to be hard for me to think of. But yeah, fine, we'll do it. Even though I feel like it's a little bit challenging. Just because, yeah, well, I'll read it to you and you'll see. This is problem 3, going back. I'm out of water. Oh no. It'll be all right. I'll live. So the per capita growth rate, or rate as people actually say that word. So the per capita growth rate of mice on an island is 2%. Let T naught equal 3. And assume that this time there are 20 mice on the island. So when T sub 0 equals 3, the number of mice, so I'm going to write that as capital M of 3 is equal to 20. Right? They say at this time there are 20 mice on the island. So M of T is equal to the number of mice at time T. Use a linear approximation to estimate the number of mice when time is equal to 3.1. So linear approximation to find the number of mice, or to approximate the number of mice at time equal to 3.1. Yeesh. Okay. So here's what I remember about linear approximations. The number of mice at time T is going to be, or time T, is going to be approximately the number of mice at the time we're given plus the derivative times the difference. Or if you prefer the graphical kind of interpretation here, right? Let me draw something on the other side here just so you guys can see this, right? I know it's been a little while. So let's say the number of mice, right? Let's say this is the number of mice. And here is T equal to 3. And here is M of 3 equal to 20. And the idea is that we're taking this tangent line, and the slope of that is M prime of 3. And we're saying instead of figuring out what instead of figuring out this value here, which is M of 3.1, what we're actually going to do is we're going to find this point on the tangent line, which is our linear approximation. So this is, I usually call this L of 3.1. And that's given by the equation of that tangent line. Well, the equation of the tangent line is exactly y minus 20 equals your slope times t minus 3. I guess I should use m. Fine. M minus 20. But just solving for this is just m of t equal to 20 plus m prime of t, right? The slope of the tangent line is the derivative at the point 3 times t minus 3, which is exactly the equation we have over here. M of 3 is 20. This here is okay, this we have to work on. We don't know what m prime of 3 is yet. It's not 2%. Because 2% isn't the rate of growth, it's the per capita rate of growth. So what does that mean? The per capita rate of growth is 2%. Well, it means that I'm sorry. So the per capita rate of growth is literally the rate of growth or the rate of change divided by the number of mice you have. So the per capita rate of growth is your derivative divided by your population. And that's equal to 2%. So I can say, oh, look, the per capita or the rate of growth of mice is equal to 2% times the number of mice. So So if I want to find the rate of growth of mice when at time equals 3, well, I'm just going to plug in t equals 3. And that's going to give me 0.02 times 20, which is going to be some number, which I can figure out in a minute here. 0.02 times 20, I think, is 0.4. My decimals are really excellent. Let's see. 2 times 20 is 40. 0.2 times 20 is 4. 0.02 times 20 is 0.4. So that means when there are 20 mice, the population is growing at 0.4 mice per whatever unit of time they're talking about. And they actually gave a unit of time. So that's going to be our slope there. There's probably a different way to think about this, but that's the way I think about it the best. But probably you can just say this is going to be your percentage, your per capita growth rate percentage times the number of mice. And then we plug in 3.1. So if we plug in 3.1, we get 20 plus 0.4 times 3.1 minus 3 is 0.1. So I get 20 plus 0.04, which is 20.04. So not a lot more mice at a tenth of a unit of time later. Okay. Then they ask us to find the actual number of mice when time equals 3.1. How do we do that? That's a really good question. Because we don't actually know what this equation is, right? How do we do that? I'm like, he's asking himself out now. So the key here is this equation. Trying to drink more water when it doesn't. So everyone should see this equation and think, I know what that means. Or maybe let me rewrite it so it's a little bit more, maybe it looks like something you've seen before. I'm going to rewrite it as dm dt is equal to 0.02 times m. When you see that the rate of growth is proportional to the population size, that is an indicator that we have exponential growth. We know that in this case, the population given as a function of time is m of t equal to c e to the kt, where k is that constant there. And she of course, she made this a little bit harder because we don't know how much we have at time 0. We know how much we have at time 3. So I know that m of 3 is equal to 20 mice. And if I plug in 3, I get c e to the 0.02 times 3. So I can solve for c. It's not pretty. It's atypical, right? Usually c would just be the initial amount. Solving for c, I get 20 divided by e to the 0.06. So then if I want to find how many mice I actually have at 3.1, m of 3.1 is going to be, well, here's my model. It's c, which is 20 over e to the 0.06 times e to the 0.02 times 3.1. And yeah, so you can simplify this a little bit. I mean, not a lot. You can simplify this as 20 times e to the, this is going to be 0.062 divided by e to the 0.06. And when you subtract those, you get e to the 0.002. So this is equal to 20 e to the 0.002, which you would leave as is. But if you actually calculate that using a calculator, which is right here, you get, let's see, hopefully you get something close to 0.02. Let's find out. E to the 0.002 times 20. So it's 20.04 because, again, all right, well, yeah. Oh, it's the same, yeah. All right, sorry. So there was 20.04 exactly. Here it's 20.04004003. So our estimate was very, very close to the actual value, which is kind of great. All right. We got 2 minutes left. Let me see. Sure. Let me do this problem because I think this next problem, this last problem we'll do, is a good question. And then I will grade your quizzes, and then I will think about when I'm going to have office hours next week. So here's problem. This is number 12 on this question. So it says consider the function f of x equal to 2 over x minus 3 minus 2 over x minus 4. And the question is true or false. There is a vertical asymptote at x equal to 4. Now, sometimes questions are just easy. This is not one of those cases. So if I saw a question like this, I would think to myself, it might be a trap, right? Like if I kind of feels like, that seems like, well, yeah, obviously it looks like there's a vertical asymptote. But I've also got this here, which is, ooh, you know what I should do? I should plug in 4 and see what happens. So I plug in 4, I definitely get 0 on the bottom. If I plug in 4, I also get 0 on top. 2 over 4 minus 3 is 2 over 1, which is 2. 2 minus 2 is 0. When you have a 0 over 0, you might have a vertical asymptote, right? Because the limit might be some sort of infinity, but you might not have a vertical asymptote. So there's 2 ways you can deal with this. The easy way, I think, is just to simplify it. So I'm going to multiply this by x minus 3 over x minus 3. When I multiply by the top, I have to distribute. So I get 2 over x minus 3 times x minus 3 minus 2 times x minus 3 over x minus 4 times x minus 3. And then if I cancel the x minus 3's here, distribute the minus 2 here, I get 2 minus 2x plus 6 over x minus 4 times x minus 3. This is a negative 2x plus 8 over x minus 4 times x minus 3. Factor out the negative 2, and we see that the x minus 4's actually cancel. So this graph does not have a vertical asymptote at x equals 4. It has a hole. I would imagine the way your teacher might actually want you to deal with this is by taking the limit. So they could say, I want you to take the limit as x approaches 4 of this thing. All right, I want to ask you guys a question that's kind of important in this last minute here. Well, okay, extra minute. What does this limit have to be so that we have a vertical asymptote at 4? Not that we have a vertical asymptote at 4, but what would it have to be for it to have a vertical asymptote? Well, think about the pictures of vertical asymptotes. If I had a vertical asymptote at 4, if I took the limit as x approaches 4, I'd be going to
infinity
or to negative infinity. Mm-hmm. So if you're saying, do I have a vertical asymptote at a point 4? The question is, does this equal some sort of infinity? If the answer is yes, then you do have a vertical asymptote. If the answer is no, and the answer is no here, you don't. So here, if you took that limit, you could still do all this algebra, and then or you could use L'Hopital's rule, but you could do all this algebra, and your limit would be negative 2 over 1, which would be negative 2. So this limit is equal to negative 2, which is not some sort of infinity. So no, we don't have a vertical asymptote. All right, that is it for me.